Hey there. Welcome back to this quiet corner of the cosmos. Tonight we explore something we can't see, but might be everywhere. A question that drifts through galaxies like a whisper. Does dark matter really exist? We see stars spin too fast. Galaxies held together by something unseen, as if there's an invisible hand guiding them. A presence with no light, no sound, just gravity's quiet pull. It's like trying to feel the wind by watching leaves move. We don't see the wind, but we see what it does. Dark matter may be the same. A silent architect, holding the universe in place. So as the night deepens, breathe slowly. Let the mystery unfold gently around you. And before we begin, tell me, where are you listening from? And what's the time now? Comment down below. Let's begin this quiet journey together. The invisible weight of the universe. Picture yourself standing in your backyard on a clear night, looking up at the Milky Way, stretching across the sky like spilled stardust. What you're seeing, every twinkling star, every wisp of cosmic cloud, represents less than 5% of everything that exists. The rest? It's invisible, undetectable by our eyes, yet somehow holding our entire galaxy together like an unseen cosmic embrace. This is the story of dark matter. And it begins with a simple observation that changed everything we thought we knew about the universe. In the 1970s, astronomer Vera Rubin was doing something that might sound mundane, but was actually revolutionary. She was measuring how fast stars move around the centers of their galaxies. What she found was so unexpected, so puzzling, that it suggested most of the universe was hiding in plain sight. Imagine a figure skater spinning with arms outstretched. As she pulls her arms in, she spins faster. This is conservation of angular momentum, a fundamental law of physics. Now imagine our galaxy as a cosmic ice rink, with the sun and all the stars we see as skaters at different distances from the center. According to everything we understood about gravity and motion, stars farther from the galactic center should move more slowly. Just like planets in our solar system, Mercury races around the sun while distant Neptune crawls at a leisurely pace. But that's not what Rubin found. Instead, she discovered that stars at the edge of galaxies were moving just as fast as those closer to the center, sometimes even faster. It was as if all the figure skaters on the cosmic rink were spinning at the same speed, regardless of how far they were from the center. This shouldn't be possible, unless there was something else there, something massive and invisible, providing the extra gravitational pull needed to keep those outer stars from flying off into the void. Think of it like watching dancers in a darkened ballroom. You can see some of the dancers illuminated by spotlights moving in elegant patterns across the floor, but their movements suggest they're dancing with partners you can't see. Invisible dancers whose presence is revealed only by the visible one's graceful turns and carefully timed steps. The visible stars in our galaxy are like those illuminated dancers, and their motion tells us about the invisible partners they're dancing with, partners made of dark matter. This cosmic choreography extends far beyond our own galaxy. Every spiral galaxy astronomers have studied shows the same peculiar behavior, from the graceful pinwheel of Andromeda to the distant galaxies visible only through powerful telescopes. They all spin faster than they should. It's as if the universe is performing a magic trick on a scale so vast it took us millennia to notice. The mathematics of this mystery are both elegant and troubling. When scientists calculate how much ordinary matter, stars, gas, dust, planets exists in a typical galaxy, they find it's only about 1/5 of what's needed to explain the observed motion. The other 4/5 must be something else entirely, something that interacts gravitationally but remains completely invisible to our instruments. It's like discovering that the majority of your house is made of rooms you can't see, can't enter, but somehow know must exist because the structure wouldn't stand without them. This invisible matter doesn't just sit quietly in the background. It forms a kind of cosmic scaffolding, a dark skeleton around which galaxies take shape. Computer simulations suggest that without this dark framework, galaxies as we know them simply couldn't exist. The ordinary matter that makes up stars and planets would have remained spread too thin throughout the universe to ever clump together into the brilliant islands of light we call galaxies. And that brings us to perhaps the most profound implication of all. If dark matter exists, then everything we can see, touch, and directly detect, every star, every planet, every grain of sand, every human being, is just cosmic foam floating on an ocean of invisible substance. We are not the main characters in the universe's story. We are tiny eddies in a vast, dark current that shapes everything around us while remaining forever beyond our direct perception. What we can't see, but still feel. There's something poetic about the idea that the most important things in the universe might be invisible, like love, or the passage of time, or the pull of memory. Dark matter reveals itself not through direct observation but through its effects on everything around it. And just like those abstract concepts that shape our lives, dark matter's influence is felt everywhere once you know how to look for it. The story of discovering dark matter is really a detective story, filled with clues that didn't quite add up and scientists who refused to accept that the universe could be so much stranger than it appeared. Long before Vera Rubin's groundbreaking observations, there were hints that something was amiss in our cosmic neighborhood. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying galaxy clusters, vast collections of hundreds or thousands of galaxies bound together by gravity like cosmic cities floating in the void. Zwicky noticed something odd about the Coma cluster, a collection of over 1,000 galaxies about 300 million light-years away. The galaxies within the cluster were moving so fast that by all rights, they should have escaped the cluster's gravitational pull long ago. It was like watching a flock of birds flying so quickly that they should have scattered to the four winds, yet somehow they remained together. Zwicky calculated that the cluster needed to be about 400 times more massive than what could be seen to hold itself together. He called this missing mass Dunkel Materie, dark matter. For decades, Zwicky's observation was treated as an interesting anomaly, a cosmic curiosity that didn't quite fit our models, but wasn't worth rebuilding our understanding of the universe over. After all, measuring the masses and velocities of distant galaxies was difficult work, prone to errors and uncertainties. Maybe Zwicky had made a mistake. Maybe there were clouds of ordinary matter we simply couldn't detect yet. Maybe gravity worked differently on such vast scales, but the clues kept accumulating, like pieces of a jigsaw puzzle that revealed an increasingly strange picture. In the 1960s and 70s, radio astronomers began mapping the distribution of hydrogen gas in galaxies. Hydrogen is the most abundant element in the universe, and it emits radio waves that can be detected across vast distances. What they found was that galaxies contained far more hydrogen than anyone expected, extending well beyond the visible edges of the galaxies themselves. This gas was moving just as mysteriously as the stars Rubin would later study, too fast to be held in place by the gravity of visible matter alone. Imagine you're listening to a symphony in a concert hall, but you can only hear the string section. The music sounds beautiful but incomplete. There are harmonies and rhythms that suggest other instruments must be playing, even though you can't hear them. The hydrogen observations were like hearing those missing instruments for the first time, revealing that galaxies had entire symphonies of matter that had been invisible to optical telescopes. The plot thickened when astronomers began studying gravitational lensing, the way massive objects bend light as it travels through space. Einstein had predicted this effect decades earlier. Just as a glass lens bends light to focus an image, massive objects like galaxies should bend the light from more distant objects behind them. When astronomers finally developed the technology to observe this cosmic lensing, they found that galaxies were bending light far more than they should, based on their visible mass. Once again, the universe seemed to be hiding most of itself from view. These early hints of dark matter's existence shared a common thread. They all suggested that gravity was the key to understanding what we couldn't see. Unlike ordinary matter, which reveals itself through electromagnetic radiation, light, radio waves, X-rays, dark matter seemed to interact only through gravity. It was like a cosmic ghost, invisible to our instruments, but capable of moving mountains or, in this case, entire galaxies. The beauty of these early discoveries lies not just in what they revealed, but in how they demonstrated the power of careful observation and mathematical thinking. Scientists couldn't see dark matter directly, but they could feel its presence through its gravitational effects, like a detective solving a case by examining fingerprints and footprints rather than eyewitness accounts. Each new observation added another piece to the puzzle, slowly painting a picture of a universe far stranger and more wonderful than anyone had imagined. And perhaps most remarkably, these discoveries suggested that the universe has been keeping its biggest secret in plain sight all along. Every time we look up at the night sky, we're surrounded by dark matter. It flows through us, around us, between the atoms in our bodies, yet it remains as elusive as a whisper in the wind. We live immersed in the universe's greatest mystery, and it took us until the late 20th century to even notice it was there. Galactic mysteries and missing mass. There's something almost magical about the way galaxies hold themselves together. Picture a cosmic carousel, spinning slowly in the vast darkness of space, its arms sweeping through the void in a dance that has continued for billions of years. Each galaxy is like an island of light in an ocean of darkness, and yet somehow these islands maintain their shape and structure, despite the incredible forces trying to tear them apart. When you really think about the physics of a galaxy, it becomes clear how remarkable their existence truly is. Our own Milky Way contains over 200 billion stars, each one racing around the galactic center at speeds that would make our fastest rockets look like leisurely strolls. The Sun, for instance, is moving at about 220 kilometers per second. That's nearly 500,000 miles per hour, as it orbits the center of our galaxy. At that speed, you could travel from New York to Los Angeles in about 20 seconds. Now imagine you're on a playground merry-go-round, spinning at tremendous speed. What keeps you from flying off? The bars you're holding on to, of course. But what are the stars in our galaxy holding on to? What invisible bars keep them from flying off into intergalactic space, never to return? This is where our models of galactic structure began to break down in the most fascinating way. When astronomers in the mid-20th century started carefully mapping the motion of stars in galaxies, they expected to find something similar to our solar system. In our solar system, the planets closer to the Sun move faster than those farther away. Mercury races around its orbit in just 88 days, while distant Neptune takes 165 years to complete one lap. This makes perfect sense given how gravity works. The closer you are to a massive object, the stronger its pull and the faster you need to move to maintain your orbit. Galaxies scientists reason should work the same way. Most of a galaxy's mass should be concentrated at its center, in a dense bulge of ancient stars and possibly a supermassive black hole. Stars near this central region should orbit quickly, while those in the outer regions should move more slowly, like cosmic tortoises compared to the inner star's rapid pace. But galaxies, it turned out, didn't read the physics textbooks. Instead of the expected gradual decrease in orbital speed with distance, astronomers found something that defied explanation. Stars in the outer regions of galaxies were moving just as fast as those closer to the center, sometimes even faster. It was as if every horse on a carousel was running at the same speed, regardless of whether it was on the inner or outer ring. This discovery was so unexpected that many scientists initially assumed it must be a measurement error. Surely there was some systematic bias in the observations, some overlooked factor that was skewing the results. But as more and more galaxies were studied, using different instruments and techniques, the same pattern emerged again and again. The rotation curves of galaxies' graphs showing how orbital speed changes with distance from the center were flat, where they should have been declining. The implications were staggering. If stars in the outer regions of galaxies were moving as fast as those closer to the center, then there had to be additional mass providing the extra gravitational pull. But where was this mass? Astronomers looked for it everywhere. In dim stars too faint to see easily, in clouds of gas and dust, in planets and asteroids and cosmic debris. They found some additional matter, but nowhere near enough to explain the observations. The numbers were unforgiving. Calculations showed that galaxies needed to be about 5 to 10 times more massive than all their visible components combined. It was like discovering that an iceberg you thought was small actually extended far deeper underwater than anyone had imagined. Except in this case, the hidden portion was completely invisible. Even more puzzling was the distribution of this missing mass. It couldn't all be concentrated at the galactic center, because that wouldn't explain why outer stars were moving so fast. Instead, the missing mass seemed to be spread throughout the galaxy, forming a vast, invisible halo that extended far beyond the visible edges of the galactic disk. It was as if each galaxy was embedded in a cocoon of invisible matter, a dark embrace that held everything together. This realization transformed our understanding of what galaxies actually are. Instead of being simple collections of stars and gas held together by their mutual gravity, galaxies appeared to be tiny visible components of much larger invisible structures. The stars and gas clouds we can see are like the foam on top of a vast dark ocean, beautiful and complex, but representing only a small fraction of what's actually there. The mystery deepened when astronomers realized that this missing mass problem wasn't limited to spiral galaxies like our own Milky Way. Elliptical galaxies, dwarf galaxies, galaxy clusters, everywhere they looked, the same pattern emerged. The universe seemed to be playing an elaborate shell game, hiding most of its mass in a form that interacted gravitationally but remained stubbornly invisible to every other form of detection. And that brings us to one of the most profound questions in modern science. If most of the matter in the universe is invisible to us, what does that say about our place in the cosmic story? Are we like bacteria on a soap bubble, unaware of the vast structures surrounding us? Or perhaps we're like the first explorers to realize that the Earth extends far beyond the horizon, standing on the shore of an ocean whose depths we're only beginning to fathom. The bullet cluster collision. Sometimes the universe provides us with natural experiments so spectacular, so perfectly designed to test our theories, that they seem almost too good to be true. The bullet cluster is one of those cosmic gifts, a collision between two massive galaxy clusters that offers us a rare glimpse into the hidden architecture of the universe. It's like watching two invisible dancers collide in slow motion, their presence revealed only by the way they disturb everything around them. About 150 million years ago, in a region of space, roughly 3.8 billion light-years from Earth, two enormous clusters of galaxies began a cosmic collision that would eventually provide some of the most compelling evidence for dark matter's existence. Galaxy clusters are among the largest gravitationally bound structures in the universe. Vast collections of hundreds or thousands of galaxies swimming in pools of hot gas, all held together by the combined gravity of both visible and dark matter. When such titans collide, the result is a cosmic catastrophe that unfolds over millions of years. But unlike the dramatic explosions we might imagine, this collision reveals itself through subtle distortions in light and the gentle separation of matter that should, by all rights, stay together. Imagine two vast crowds walking toward each other in a dense fog. As they pass through each other, most people in each crowd continue on their original path. The crowds are mostly empty space. After all, so direct collisions are rare. But now imagine that each crowd is surrounded by an invisible sea of something thick and sticky, like cosmic honey. As the crowds pass through each other, these invisible seas collide and stick together, creating drag and turbulence that separates them from the people they were originally traveling with. This is essentially what happened in the bullet cluster collision. Except the crowds were galaxies, and the cosmic honey was hot gas and dark matter. When the two clusters collided, several different types of matter behaved in completely different ways, creating a natural experiment that allowed astronomers to study dark matter's properties like never before. The galaxies themselves, being mostly empty space punctuated by stars, passed through each other relatively unaffected, like ghosts walking through walls. The hot gas that permeates galaxy clusters, however, experienced tremendous friction during the collision. This gas, heated to millions of degrees and glowing in X-ray wavelengths, slowed down and became separated from the galaxies it once surrounded. The collision created shockwaves in this gas, heating it even further and causing it to glow brighter in X-rays, creating a bullet-like shape that gives the cluster its name. But here's where the story becomes truly remarkable. When astronomers used gravitational lensing to map the total mass of the colliding clusters, they found that most of the mass had traveled with the galaxies, not with the hot gas. This was the smoking gun that dark matter advocates had been hoping for. Direct evidence that most of the matter in the universe doesn't interact electromagnetically, like ordinary matter does. The beauty of the bullet cluster lies in how it separates different types of matter based on their physical properties. The hot gas, being made of ordinary matter, experiences electromagnetic forces and friction during the collision, causing it to slow down and lag behind. Dark matter, interacting only through gravity, passes through the collision largely unaffected, like two streams of cosmic ghosts flowing through each other without resistance. This separation creates a natural controlled experiment. If dark matter didn't exist, and the missing mass problem was actually due to our misunderstanding of gravity, then the gravitational effects should follow the hot gas after all. That's where most of the ordinary matter ended up. But instead, the gravitational lensing maps show that most of the mass traveled with the galaxies, in regions where very little ordinary matter exists. It's like watching a magic trick where the magician accidentally reveals the secret. The collision has literally pulled apart the different components of these galaxy clusters, showing us that there really is invisible matter distinct from the hot gas we can see with X-ray telescopes. The dark matter has left its fingerprints all over the crime scene, bending light from background galaxies in ways that reveal its presence and distribution. The bullet cluster also tells us something important about dark matter's properties. The fact that the dark matter halos of the two clusters passed through each other with minimal disruption suggests that dark matter particles rarely if ever collide with each other. They're not just invisible to light, they're nearly invisible to each other as well, interacting so weakly that even when concentrated into the dense cores of galaxy clusters, they can pass through each other like cosmic ghosts. This ghostly behavior sets dark matter apart from every form of matter we're familiar with. Ordinary matter is sociable. Particles bump into each other, exchange energy, heat up, cool down, clump together and spread apart based on temperature and pressure. Dark matter, by contrast, seems to live in a parallel universe of pure gravity, responding only to the geometric curvature of spacetime, while remaining aloof from all the electromagnetic drama that governs the behavior of ordinary matter. The implications extend far beyond this single cosmic collision. If dark matter behaves this way in the bullet cluster, it likely behaves the same way throughout the universe, flowing through space like an invisible river that shapes the distribution of galaxies without ever directly touching the ordinary matter they contain. We live immersed in this dark current, unaware of its presence, except through careful measurements of its gravitational effects. And perhaps most remarkably, the bullet cluster reminds us that the universe is far more transparent than we ever imagined. What we see as solid, impenetrable structures, galaxy clusters containing the mass of quadrillions of suns, are actually mostly empty space through which invisible rivers of dark matter flow freely. The collision that created the bullet cluster happened 150 million years ago, but its light is just reaching us now, carrying news of a cosmic experiment that teaches us about the hidden nature of reality itself. Lensing the void. Light, we often think, travels in straight lines from the sun to Earth, from distant stars to our telescopes, carrying information across the vast emptiness of space, with perfect fidelity. But Einstein taught us that space itself can bend, and where space bends, light must follow those curves like a marble rolling along a warped surface. This cosmic curvature has given us one of our most powerful tools for detecting the invisible. Gravitational lensing, the universe's way of revealing what cannot be seen directly. Imagine you're walking through a dense forest at night, using only a flashlight to navigate. Most of the trees are invisible beyond your beam, but occasionally you notice your light bending around unseen obstacles, creating strange shadows and bright spots that reveal the presence of trees you cannot see. Gravitational lensing similarly, except instead of trees bending flashlight beams, massive concentrations of matter bend the light from distant galaxies, creating cosmic mirages that reveal the presence of invisible dark matter. The physics behind this phenomenon is both elegant and mind-bending. According to Einstein's general theory of relativity, mass and energy warp the fabric of spacetime itself. Just as a heavy ball placed on a stretched rubber sheet creates a depression that causes smaller balls to roll toward it, massive objects in space create gravitational wells that bend the paths of light rays passing nearby. The more massive the object, the more dramatic the bending. When astronomers point their telescopes toward distant galaxy clusters, they often notice something peculiar about the background galaxies visible behind them. These distant galaxies appear stretched, distorted, sometimes even multiplied into multiple images arranged in arc-like patterns around the cluster. It's as if the cluster is acting like a cosmic funhouse mirror, warping and magnifying the light from galaxies billions of light-years beyond it. But here's where the story becomes detective work of the highest order. When scientists carefully analyze these distortions, they can work backward to determine exactly how much mass is present in the lensing cluster, and how that mass is distributed. It's like being able to determine the shape and size of an invisible lens by studying how it distorts the images seen through it. What they consistently find is remarkable and troubling in equal measure. The amount of lensing observed requires far more mass than can be accounted for by all the visible matter in the galaxy cluster, all the stars, hot gas, dust, and debris combined. Once again, the universe is hiding most of itself from direct view, revealing its presence only through its gravitational effects on light. The precision of these measurements is truly extraordinary. Modern space telescopes can detect lens distortions so subtle that the shapes of background galaxies are changed by only a few percent. Distortions invisible to the naked eye, but measurable with careful analysis. It's like detecting the presence of an invisible person by noticing that raindrops fall slightly differently when they pass near them. Some of the most dramatic examples of gravitational lensing create what astronomers call Einstein rings. Perfect or near-perfect circles of light formed when a massive object lies directly between Earth and a more distant light source. These cosmic rings are like fingerprints left by invisible matter, beautiful and ethereal signatures of the universe's hidden mass. But gravitational lensing reveals more than just the presence of dark matter. It maps its distribution with unprecedented detail, unlike other detection methods that can only tell us the total amount of missing mass. Lensing allows astronomers to create detailed maps showing exactly where dark matter is concentrated and where it's more sparse. These maps reveal that dark matter forms vast, interconnected webs throughout the universe, with galaxies strung along the densest filaments like pearls on invisible strings. The technique has become so sophisticated that astronomers can now perform weak lensing studies, detecting the subtle statistical distortions in the shapes of millions of background galaxies to map dark matter on cosmic scales. It's like having X-ray vision for the universe, allowing us to see through the bright facade of stars and galaxies to the dark scaffolding beneath. Perhaps most remarkably, gravitational lensing provides a completely independent confirmation of dark matter's existence. Unlike rotation curve measurements, which rely on our understanding of stellar dynamics, or X-ray observations, which depend on the physics of hot gas, lensing depends only on Einstein's general relativity, one of the most thoroughly tested theories in physics. When light bends more than visible matter can account for, we know with mathematical certainty that additional mass must be present. This convergence of evidence from multiple independent techniques creates a compelling case for dark matter's reality. It's like solving a mystery where multiple witnesses, using completely different methods, all point to the same conclusion. The rotation curves of galaxies, the dynamics of galaxy clusters, and the bending of light all tell the same story. The universe contains vast amounts of invisible matter that reveals itself only through gravity, and that brings us to a profound realization about the nature of reality itself. Light, the very medium through which we perceive the universe, is constantly being bent and shaped by invisible forces. Every photon that reaches our telescopes from distant galaxies has traveled through an invisible landscape of dark matter, its path subtly deflected by gravitational fields we cannot see. In a very real sense, dark matter is constantly rewriting the story the universe tells us about itself, editing the cosmic narrative in ways we're only now learning to detect and decode. The universe, it seems, is not just stranger than we imagine, it's stranger than we can see. But through the elegant mathematics of bent light and warped space, we're slowly learning to read the invisible writing that dark matter leaves across the cosmic sky. The echoes of the Big Bang. If you could rewind the universe like a cosmic movie, playing it backward through billions of years of expansion and evolution, you would eventually reach a moment of extraordinary significance. A time when the entire observable universe was smaller than an atom, hotter than the core of any star, and so dense that matter and energy existed in forms we can barely comprehend. This was the beginning, the Big Bang, and remarkably we can still hear its echoes today. About 380,000 years after that initial moment of creation, the universe had expanded and cooled enough for something magical to happen. For the first time, electrons and protons could combine to form neutral hydrogen atoms without being immediately torn apart by the intense heat. This moment, called recombination, was like the universe taking its first clear breath. Suddenly, light could travel freely through space, without being constantly scattered by free electrons. The universe became transparent, and the afterglow of that moment still fills every corner of space today. This afterglow is called the cosmic microwave background, or CMB, and it's one of the most important pieces of evidence we have for understanding the early universe, including the role that dark matter played in shaping everything we see today. When we tune a radio between stations and hear that faint static, about 1% of that hiss is actually the sound of creation itself. The stretched and cooled radiation from the Big Bang still washing over us after nearly 14 billion years. But the cosmic microwave background is more than just a fossil from the early universe. It's a baby picture of reality itself, showing us what the cosmos looked like when it was only 380,000 years old. And like any good baby picture, it reveals family resemblances and hints about how the subject would grow and develop over time. When scientists first detected the CMB in the 1960s, they expected it to be perfectly smooth and uniform, reflecting a universe that began in a state of perfect simplicity. But as measurement techniques improved, they began to notice something extraordinary. The cosmic microwave background wasn't perfectly smooth at all. Instead, it contained tiny variations in temperature. differences of only a few millionths of a degree, scattered across the sky in a complex pattern that looked almost like cosmic fingerprints. These minute temperature variations tell an incredible story. They represent tiny density fluctuations in the early universe, regions that were just slightly denser or less dense than average. In the 13.8 billion years since recombination, gravity has been amplifying these fluctuations, turning small density differences into the cosmic web of galaxies, clusters, and vast empty voids we see today. Every galaxy, every star system, every planet, including Earth, can trace its ancestry back to these primordial ripples in the fabric of space and time. But here's where dark matter enters the story in the most crucial way imaginable. Without dark matter, these tiny fluctuations in the early universe wouldn't have been enough to grow into the large-scale structures we observe today. Gravity is a weak force, and ordinary matter faces an additional challenge. As it tries to clump together under its own gravity, the radiation pressure from the intense heat of the early universe pushes back, preventing ordinary matter from collapsing into dense concentrations. Dark matter, however, doesn't interact with light or radiation. While ordinary matter was locked in a cosmic tug-of-war between gravity and radiation pressure, dark matter was free to begin collapsing under its own gravity immediately after the Big Bang. Like an invisible scaffolding, dark matter created the framework upon which ordinary matter could later accumulate once the universe had cooled enough for radiation pressure to weaken. The precise pattern of temperature variations in the cosmic microwave background provides a detailed test of this scenario. Scientists can use supercomputers to simulate how the early universe should have evolved with different amounts of dark matter, ordinary matter, and dark energy. Then compare these simulations to the actual observed pattern of the CMB. The agreement is remarkable. The data matches perfectly with a universe that is about 27% dark matter, 5% ordinary matter, and 68% dark energy. It's like having a recipe for the universe written in the language of ancient light. The cosmic microwave background tells us not just that dark matter exists, but exactly how much of it there is, and how it was distributed in the early universe. Every detail of the CMB's pattern, the size of the hot and cold spots, their distribution across the sky, the precise amplitude of the temperature variations depends on the fundamental properties of dark matter and its role in cosmic evolution. But the CMB reveals something even more profound about dark matter's nature. The fact that dark matter began clumping immediately after the Big Bang, while ordinary matter remained smooth for hundreds of thousands of years longer, explains why dark matter halos formed first, and why galaxies today are embedded within these invisible structures. It's not that dark matter invaded galaxies after they formed. Rather, dark matter created the gravitational wells into which ordinary matter later fell. This temporal sequence, dark matter first, ordinary matter later, is written into the cosmic microwave background like a prehistoric record of how the universe learned to build itself. The pattern we see in the CMB is the shadow cast by invisible matter onto the last surface of scattering, a cosmic fossil that preserves the moment when light and matter went their separate ways for the first time. And that brings us to perhaps the most poetic aspect of studying the cosmic microwave background. Every time we measure this ancient light, we're literally looking backward in time, seeing the universe as it was when it was younger than 1,000,000 years old. The photons hitting our detectors today have been traveling through space for nearly the entire age of the universe, carrying information about cosmic conditions from an era when the first stars had not yet been born, and galaxies were still just dreams in dark matter's gravitational embrace. The echoes of the Big Bang remind us that we live in a universe with a history, a cosmos that has grown and evolved from simple beginnings into the complex, beautiful, and mysterious place we call home. And woven throughout that history, from the very beginning, is the invisible thread of dark matter shaping, guiding, and enabling everything we see today. Cold, warm, or hot. In the strange world of dark matter physics, temperature isn't about whether you need a sweater, it's about speed, and speed determines everything. When scientists classify dark matter as cold, warm, or hot, they're talking about how fast these invisible particles were moving in the early universe. And this seemingly simple property completely changes how cosmic structures form and evolve over billions of years. Imagine 3 different types of cosmic seeds scattered throughout the early universe, each destined to grow into the galaxies and galaxy clusters we see today. Some seeds are sleepy and slow-moving, content to settle down wherever they find themselves and gradually accumulate more matter through their gravitational pull. Others are energetic wanderers, zipping around so quickly that they wash out small-scale structure, preventing the formation of anything but the largest cosmic structures, and then there are seeds that fall somewhere in between. Active enough to smooth out the tiniest fluctuations but calm enough to allow medium-sized structures to form. Cold dark matter represents the first scenario. Particles that were moving slowly, or non-relativistically, in the early universe. These hypothetical particles would have settled into gravitational wells quickly, allowing structures to form from the bottom up, with small clumps merging to form larger ones over cosmic time. It's like watching a gentle snowfall accumulate into drifts, then larger mounds, and eventually into towering snowbanks through the patient work of gravity. The cold dark matter model has been remarkably successful at explaining the large-scale structure of the universe. Computer simulations based on cold dark matter produce cosmic webs that look strikingly similar to what we observe: vast filaments of matter intersecting at nodes where galaxy clusters form, separated by enormous voids where very little matter exists. These simulations can reproduce the statistical properties of galaxy clustering, the abundance of galaxy clusters, and the overall architecture of the cosmic web with impressive accuracy. But cold dark matter isn't perfect. On smaller scales, the theory predicts more structure than we actually observe. Simulations suggest there should be thousands of small dark matter halos orbiting our Milky Way, but we only see a few dozen dwarf galaxies. This is known as the missing satellites problem, and it's one of several small-scale puzzles that keep cosmologists awake at night, wondering if our understanding of dark matter is incomplete. Hot dark matter tells a very different story. These would be particles that were moving at close to the speed of light in the early universe. Particles like neutrinos, which we know exist and have tiny but non-zero masses. The problem with hot dark matter is that these speedy particles would have erased small-scale structure entirely, streaming out of small gravitational wells faster than gravity could hold them back. In a universe dominated by hot dark matter, galaxies could never have formed. Only the larger structures like galaxy clusters and superclusters would exist. The mathematics of this streaming effect are both beautiful and frustrating. Particles moving at high speeds have what physicists call a free streaming length, a characteristic distance over which they smooth out density fluctuations. For truly hot dark matter, this length is so large that nothing smaller than galaxy clusters could survive. It's like trying to build sandcastles on a beach, where the waves are so powerful that they wash away any structure smaller than a mountain. Observations ruled out hot dark matter as the dominant component of the universe's missing mass decades ago. While neutrinos certainly exist and contribute to the universe's total mass budget, they can't account for more than a small fraction of the dark matter we observe. The universe simply has too much small-scale structure, too many galaxies, too many dwarf galaxies, too much complexity on scales where hot dark matter would have erased everything. Warm dark matter occupies the middle ground, representing particles that were moving at intermediate speeds in the early universe. These particles would have erased the smaller structures while preserving larger ones, potentially solving some of the problems that plague cold dark matter models. Warm dark matter could explain why we don't see as many small satellite galaxies as cold dark matter predicts, while still allowing the formation of the cosmic web we observe. The temperature classification also reveals something profound about the relationship between particle physics and cosmology. The speed at which dark matter particles were moving in the early universe depends on their mass and the temperature of the cosmic plasma they were immersed in. Heavier particles move more slowly at a given temperature, while lighter particles zip around more energetically. This connection means that determining the temperature of dark matter isn't just an abstract exercise, it's a way of probing the fundamental properties of these invisible particles. If we could definitively determine whether dark matter is cold, warm, or hot, we would learn something crucial about the mass and interactions of dark matter particles, providing vital clues for the experimental physicists trying to detect them in laboratories here on Earth. The beauty of this temperature-based classification system lies in how it connects the smallest scales of particle physics to the largest scales of cosmic structure. The mass of a single dark matter particle, something so tiny it might never interact with ordinary matter throughout the entire age of the universe, determines whether dwarf galaxies can form, whether the cosmic web has its observed level of detail, and whether the universe develops the kind of rich hierarchical structure that allows places like Earth to exist. Recent observations from ever more sensitive telescopes are beginning to provide new constraints on dark matter's temperature. Studies of the Lyman alpha forest, a pattern of absorption lines in the spectra of distant quasars, suggests that dark matter can't be too warm, because we see structure on scales that would have been erased by highly energetic particles. Similarly, observations of the smallest, faintest galaxies are helping to determine whether cold dark matter's predictions for small-scale structure are correct. And that brings us to one of the most intriguing possibilities in modern cosmology. What if dark matter isn't purely cold, warm, or hot, but some combination of different particle types? Perhaps the universe's dark matter consists of multiple species of invisible particles, some cold and some warm, each contributing to the cosmic story in its own way. Such a mixed dark matter scenario could potentially solve several puzzles at once, explaining both the large-scale success of cold dark matter and its small-scale challenges. The temperature of dark matter ultimately tells us a story about cosmic evolutionitis, about how the universe grew from a smooth, nearly featureless beginning into the rich tapestry of galaxies, stars, and planets we see today. Whether that story unfolds through the patient accumulation of cold particles, the structure-smoothing flow of hot particles, or some more complex combination, the temperature of the invisible universe continues to shape everything we can see. Neutrinos and other shadows. In the basement of the Kamioka mine in Japan, 1,000 meters beneath the surface of the Earth, sits one of the most extraordinary scientific instruments ever built. The Super Kamiokande detector is a cathedral-sized tank filled with ultra-pure water, surrounded by thousands of sensitive light detectors, all designed to catch the faintest whisper of particles so elusive they can pass through the entire planet, as if it were made of empty space. These are neutrinos, the universe's most abundant, massive particles, and our closest analogy to what dark matter might be like. Every second, trillions of neutrinos pass through your body without you feeling the slightest thing. They stream through the Earth, through buildings, through mountains, through the cores of stars, interacting so rarely with ordinary matter that they might as well exist in a parallel universe. In many ways, neutrinos were our first glimpse into the invisible cosmos, a preview of what it might mean for most of the universe to be made of something we can barely detect. The story of neutrinos begins with a mystery that puzzled physicists for decades. In the early 20th century, scientists studying radioactive decay noticed that energy seemed to be disappearing. Reactions that should have conserved energy perfectly appeared to be losing some in the process. Either the fundamental laws of physics were wrong, or something invisible was carrying away the missing energy. Wolfgang Pauli, one of the pioneers of quantum mechanics, made a bold prediction in 1930. There must be a new type of particle, nearly massless, and almost completely non-interacting, that carries away the missing energy in radioactive decay. He called it the neutrino, Italian for little neutral one, and joked that he had done a terrible thing by postulating a particle that could never be detected. It took 26 years to prove Pauli wrong about the detection part, but he was absolutely right about the particle. Neutrinos are indeed nearly massless, electrically neutral, and interact so weakly with ordinary matter that a neutrino could pass through a light year of lead without being stopped. They come in 3 varieties or flavors: electron neutrinos, muon neutrinos, and tau neutrinos, and they have the strange quantum mechanical property of oscillating between these flavors as they travel through space. For decades, neutrinos were thought to be completely massless, like photons. But beginning in the 1990s, a series of groundbreaking experiments revealed that neutrinos do have mass, tiny masses, but masses nonetheless. This discovery was revolutionary because it proved that the standard model of particle physics, our best theory of fundamental particles and forces, was incomplete. It also raised an intriguing possibility. Could neutrinos be the dark matter that astronomers had been seeking? The numbers were tantalizing. The universe is filled with neutrinos, relics from the Big Bang, that permeate every cubic centimeter of space. If these ancient neutrinos had even tiny masses, they could potentially account for the missing matter in galaxies and galaxy clusters. It would be an elegant solution, explaining dark matter in terms of particles we knew existed rather than requiring entirely new physics. But as scientists studied the implications more carefully, they realized that neutrinos, while certainly contributing to the universe's total mass, couldn't be the primary component of dark matter. The problem goes back to the temperature classification we discussed earlier. Neutrinos are hot dark matter, moving at speeds close to the speed of light in the early universe. Hot dark matter would erase small-scale structure, preventing the formation of individual galaxies, and leaving us with a universe containing only the larger structures like galaxy clusters. Computer simulations of cosmic evolution confirmed this conclusion. In universes dominated by neutrino dark matter, galaxies simply don't form. The small density fluctuations that eventually grew into galaxies would be washed out by the rapid motion of neutrinos streaming from regions of high density to regions of low density. We know from observations that the universe contains abundant small-scale structure, so neutrinos can contribute at most a small fraction of the total dark matter budget. Yet, neutrinos remain important for several reasons. First, they prove that invisible weakly interacting particles do exist in nature. Existence proves that the concept of dark matter isn't completely crazy. Second, precision measurements of neutrino masses and their contribution to cosmic structure provide important constraints on cosmological models. And third, the techniques developed to detect neutrinos have influenced the design of experiments searching for other dark matter candidates. The study of neutrinos also reveals something beautiful about the interconnectedness of physics. These particles, born in nuclear reactions in the cores of stars, in cosmic ray collisions in the upper atmosphere, and in the primordial furnace of the Big Bang itself, carry information about processes occurring in the most extreme environments in the universe. Every neutrino that passes through the detectors buried deep beneath the Earth's surface tells a story about stellar nucleosynthesis, cosmic ray interactions, or the fundamental properties of matter and energy. But perhaps most importantly, neutrinos teach us about the limits of our perception. Just as early studies of neutrinos revealed that the universe contains vast numbers of particles we can barely detect, the search for dark matter may be revealing that reality extends far beyond what we can directly observe. We live immersed in streams of particles we cannot see, feel, or touch. Yet these invisible rivers shape the evolution of galaxies and may determine the ultimate fate of the universe itself. The neutrino story reminds us that nature often hides its most important secrets in plain sight. For decades, physicists knew that energy was disappearing in radioactive decay, but it took extraordinary insight to realize that this wasn't a failure of physics, but a hint about invisible particles streaming away from every nuclear reaction. Similarly, the gravitational anomalies that led to the dark matter hypothesis might be pointing us toward new particles or phenomena that exist all around us, waiting to be discovered by the right combination of theoretical insight and experimental ingenuity. As we continue to search for dark matter, neutrinos serve as both inspiration and cautionary tale. They show us that the universe can indeed be filled with invisible matter that reveals itself only through subtle effects. But they also remind us that the solution to cosmic mysteries is rarely as simple as we first hope. The universe, it seems, delights in being just transparent enough to tantalize us with glimpses of its hidden depths, while remaining opaque enough to keep us searching for deeper truths. The WIMP hypothesis. In the pantheon of acronyms that populate modern physics, few are as evocative as WIMP. Weakly interacting massive particles. There's something almost poetic about the name, suggesting particles that are both substantial and shy, massive enough to shape the cosmos yet so retiring that they barely acknowledge the existence of ordinary matter. For decades, WIMPs have been the leading candidates for dark matter, representing what many scientists consider the most elegant solution to the universe's greatest mystery. The WIMP hypothesis emerges from what physicists call the WIMP miracle, a remarkable convergence of numbers that seems too perfect to be mere coincidence. Imagine you're trying to explain why the universe contains roughly 5 times more dark matter than ordinary matter. You might expect this to require some incredibly specific, fine-tuned properties for dark matter particles. But WIMPs naturally produce approximately the right abundance through a beautiful dance of particle physics and cosmology. The story begins in the early universe, when temperatures were so high that matter and energy existed in forms we can barely imagine. In this primordial furnace, particles and antiparticles of all types were constantly being created and destroyed in pairs, existing in what physicists call thermal equilibrium. Dark matter particles, if they were WIMPs, would have been part of this cosmic dance, appearing and disappearing as the universe's energy fluctuated around them. But as the universe expanded and cooled, something crucial happened. The temperature dropped below the threshold needed to create new WIMP, anti-WIMP pairs, but the existing particles continued to annihilate with each other, gradually reducing their numbers. Eventually, the universe became so sparse that WIMPs could no longer easily find their antiparticle partners to annihilate with, and their abundance froze out at whatever level existed at that moment. Here's where the miracle occurs. If you calculate how many WIMPs should survive this freeze-out process, assuming they have the interaction strength suggested by certain extensions of the standard model of particle physics. You get approximately the right amount to explain dark matter. It's as if the universe conspired to produce exactly the amount of invisible matter needed to form galaxies, without requiring any special fine-tuning of particle properties. This connection between particle physics and cosmology represents one of the most beautiful examples of how the very small and the very large inform each other. The properties of hypothetical particles that might fit in the palm of your hand, if you could somehow hold them, determine the large-scale structure of the entire observable universe. The same mathematical frameworks that describe how particles behave in laboratory accelerators also govern the formation of galaxy clusters spanning millions of light-years. WIMPs also offer an appealing explanation for why dark matter has remained hidden for so long. If these particles interact with ordinary matter only through the weak nuclear force, the same force responsible for certain types of radioactive decay, then they would be extraordinarily difficult to detect directly. The weak force lives up to its name, operating over such short distances and with such feeble strength that weak interactions are exceedingly rare. To put this in perspective, imagine a WIMP particle traveling through a block of lead, a light-year thick. Even with that enormous amount of material, the WIMP would have only about a 50-50 chance of interacting with a single lead nucleus. This ghostly behavior explains why dark matter can permeate ordinary matter without us noticing, and why detecting it requires such extraordinary experimental techniques. The search for WIMPs has driven some of the most sophisticated experiments in modern physics. Deep underground, shielded from cosmic rays and other sources of background radiation, physicists have built detectors containing hundreds of kilograms of ultra-pure materials, cooled to temperatures just above absolute zero, and monitored by electronics sensitive enough to detect the recoil of a single atomic nucleus. The idea is elegantly simple. If WIMPs occasionally collide with ordinary matter, they should impart a tiny amount of energy to atomic nuclei, causing them to recoil like billiard balls struck by invisible cues. These recoils would produce minute amounts of heat, light, or electrical charge, that could be detected by sufficiently sensitive instruments. It's like trying to detect ghostly pool players by watching for the seemingly spontaneous movement of billiard balls. But after decades of increasingly sensitive searches, WIMPs have remained frustratingly elusive. Each experiment has pushed the limits of detection to new extremes, constraining the possible properties of WIMP dark matter more and more tightly, yet no definitive signal has emerged. This has led to what some physicists call the WIMP crisis, the growing tension between the theoretical appeal of WIMPs and the experimental difficulty of finding them. The absence of a clear WIMP signal doesn't necessarily mean these particles don't exist. Perhaps they interact even more weakly than theoretical models suggest, requiring detectors that are larger, more sensitive, or operate on longer timescales than current technology allows. Or perhaps WIMPs interact with ordinary matter in ways that current experiments aren't designed to detect. Alternatively, the null results might be pointing us toward a more profound conclusion, that dark matter isn't made of WIMPs at all, but of something even stranger and more exotic. The universe has surprised us before with its creativity in hiding its secrets, and there's no guarantee that the most theoretically appealing solution is the correct one. The WIMP hypothesis has also inspired searches beyond terrestrial laboratories. If dark matter particles can annihilate with each other, as suggested by the thermal freeze-out scenario, then regions of space with high dark matter concentrations should produce detectable signals from the annihilation products. Astronomers have looked for these signals: excess gamma rays, positrons, or other high-energy particles coming from the center of our galaxy, from dwarf galaxies or from galaxy clusters. And that brings us to one of the most intriguing aspects of the WIMP hypothesis. It suggests that the same particles responsible for shaping cosmic structure might also be detectable through their own self-destruction. The idea that dark matter might literally illuminate itself through annihilation has a certain poetic justice, as if the universe's most elusive component might eventually reveal itself through its own demise. Whether or not WIMPs turn out to be the solution to the dark matter mystery, they represent something important about how science progresses. The WIMP hypothesis emerged from the intersection of particle physics and cosmology, demonstrating how seemingly unrelated fields can inform and enrich each other. Even if WIMPs don't exist, the search for them has advanced our understanding of both particle detection techniques and the fundamental nature of matter and energy. The story of WIMPs reminds us that the most elegant scientific theories are often those that connect different scales and phenomena through simple, underlying principles. Whether these particular invisible particles exist or not, the search for them continues to push the boundaries of human knowledge and technological capability, bringing us closer to understanding our place in the cosmic story. Actions and the elegant solution. Sometimes the most beautiful solutions in physics emerge not from trying to solve the problem you're working on, but from attempting to resolve a completely different puzzle. The action represents one of those serendipitous discoveries, a hypothetical particle originally conceived to solve a thorny problem in quantum chromodynamics, that turned out to be an unexpectedly elegant candidate for dark matter. The story begins with what physicists call the strong CP problem, a mouthful of technical jargon that masks one of the deepest mysteries in particle physics. Without diving too deeply into the mathematical weeds, the issue is this: the equations that describe the strong nuclear force, the force that holds protons and neutrons together in atomic nuclei, contain a term that should violate certain fundamental symmetries of nature. These violations should produce measurable effects, particularly in the behavior of neutrons, but when physicists look for these effects they find nothing. It's like discovering that the blueprints for a building include a feature that should make the structure lean dramatically to one side. But when you look at the actual building it stands perfectly straight. Either there's something wrong with the blueprints, or there's some hidden mechanism keeping the building upright that you haven't accounted for yet. In 1977, physicist Roberto Pecchier and Helen Quinn proposed an elegant solution. What if there's a new field permeating all of space that dynamically adjusts itself to cancel out the unwanted term in the strong force equations? This field would be like an invisible counterweight that automatically balances the building, keeping it upright no matter what forces try to tilt it. But quantum field theory tells us that every field should have an associated particle, and this new field would be no exception. The particle associated with the Pecchier-Quinn field was dubbed the axion by physicist Frank Wilczek, who named it after a brand of laundry detergent because it cleaned up the strong CP problem. It was a moment of scientific humor that captured something important about how theoretical physics works. Sometimes the most profound insights come wrapped in unexpected packages. When physicists began calculating the properties that axions should have, they discovered something remarkable. These particles would be extraordinarily light, potentially trillions of times lighter than electrons, and would interact with ordinary matter so weakly that they might as well be ghosts. They would be produced copiously in the early universe, and would persist essentially forever, creating a cosmic sea of invisible particles that could pervade every corner of space. The numbers were tantalizing. Depending on exactly how light actions are, and when they began oscillating in the early universe, they could potentially account for all of the dark matter we observe today. Unlike WIMPs, which require specific assumptions about particle physics beyond the standard model, actions emerge naturally from attempts to solve known problems within our current theoretical framework. But perhaps most beautifully, actions would behave very differently from any other dark matter candidate. Instead of consisting of individual particles zipping around like invisible billiard balls, action dark matter would form coherent waves, quantum fields oscillating in unison across vast regions of space. It would be less like a swarm of invisible bees and more like a cosmic symphony, with different regions of space humming at slightly different frequencies. This wave-like behavior leads to some fascinating possibilities. If action dark matter exists, then we're not just surrounded by invisible particles, we're immersed in invisible waves, oscillating fields that permeate our bodies and everything around us. These fields might even interact with electromagnetic fields in subtle ways, potentially converting into detectable photons under the right conditions. The experimental search for actions has led to some of the most creative detector designs in physics. The most promising approach uses what's called the Primakov effect, the theoretical possibility that actions might convert into photons when they encounter strong magnetic fields. Scientists have built action haloscopes, cavity resonators placed within powerful magnets, designed to detect the faint microwave radiation that might be produced if action dark matter converts to electromagnetic waves. Imagine tuning a cosmic radio, slowly scanning through frequencies in search of a signal that might be the universe's dark matter revealing itself through its conversion to ordinary light. The search requires extraordinary sensitivity and patience, as the expected signal would be incredibly faint, like trying to detect a whisper in a room full of shouting voices. Other experimental approaches have looked for actions produced in the laboratory or streaming from the sun. The CAST experiment at CERN points a powerful magnet toward the sun, searching for X-rays that might be produced if solar actions convert to photons in the Earth's magnetic field. It's like having X-ray vision for invisible particles. attempting to see through the sun's exterior to detect the actions that should be produced in its core. The search for actions also connects to some of the most extreme environments in the universe. Neutronium stars, incredibly dense stellar remnants where matter exists in forms that can't be replicated on Earth, should be prolific action producers. If these particles exist, the intense magnetic fields around neutron stars might convert these actions back into detectable radiation, potentially allowing astronomers to study dark matter through telescope observations rather than underground experiments. What makes actions particularly appealing as dark matter candidates is how they naturally explain several puzzling observations about cosmic structure. Unlike WIMPs, which should clump together on small scales, axion dark matter would remain smooth on scales smaller than the de Broglie wavelength of the axion field, potentially explaining why we don't see as much small-scale structure as some models predict. The wave-like nature of axion dark matter also leads to fascinating predictions about how it should behave in galaxy halos. Instead of forming smooth spherical distributions, axion dark matter might create complex interference patterns, with regions of constructive and destructive interference that could affect the distribution of ordinary matter in subtle but detectable ways. And that brings us to perhaps the most poetic aspect of the axion hypothesis: the idea that dark matter might not be particulate at all, but rather a fundamental field that fills all of space. We would be living not just in a universe populated by invisible particles, but in a universe where the very fabric of space is oscillating with invisible waves, a cosmic ocean of dark energy that shapes everything we see, while remaining forever, just beyond our direct perception. Whether axions exist or not, their story illustrates something beautiful about how physics progresses. Solutions to one problem often reveal unexpected connections to completely different mysteries, and the search for fundamental understanding frequently leads us down paths we never expected to travel. The axion reminds us that the universe's greatest secrets might be hidden not in exotic, hard-to-understand phenomena, but in elegant solutions to problems we thought we already understood. Supersymmetry and the search for balance. There's something almost mystical about the idea of supersymmetry, a theoretical framework that suggests every particle in the universe has an invisible twin, a shadow companion that mirrors its properties, while remaining hidden from our direct observation. If supersymmetry is real, then the familiar particles that make up atoms, light, and forces represent only half of nature's fundamental cast of characters. The other half exists in a parallel realm of superpartners, waiting to be discovered by experiments powerful enough to probe the deepest layers of reality. The concept of supersymmetry emerged from theoretical physics in the 1970s, as physicists wrestled with some of the most profound questions about the nature of matter and energy. Why do fundamental particles have the masses they do? Why are the forces of nature so different in strength? Why does the universe seem fine-tuned for the existence of atoms, stars, planets, and life itself? Supersymmetry offers elegant answers to all of these questions, but at the cost of doubling the number of fundamental particles in the universe. Imagine looking at your reflection in a perfect mirror, but instead of seeing an exact copy of yourself, you see a figure that shares your essential characteristics, but appears completely different, perhaps translucent or glowing with a faint inner light, or existing slightly out of phase with ordinary reality. This is roughly analogous to how supersymmetry works. Every familiar particle has a superpartner that shares certain quantum properties, but differs in other crucial ways. The electron, for instance, would be paired with a particle called the selectron. Quarks, the constituents of protons and neutrons, would have squark partners. Photons would be accompanied by photons. The names sound like something from science fiction, but they represent serious theoretical possibilities that could revolutionize our understanding of the universe's fundamental structure. What makes supersymmetry particularly appealing as a source of dark matter candidates is that it naturally produces particles with exactly the properties we expect dark matter to have. The lightest supersymmetric particle, often called the LSP, would be stable because of conservation laws specific to supersymmetric theories, electrically neutral, and interact only weakly with ordinary matter. In many supersymmetric models, this particle is the neutralino, a quantum mechanical mixture of several different types of superpartners that would make an ideal WIMP. The mathematics of supersymmetry possess an almost musical elegance. The theory introduces a new type of symmetry that maps particles with different intrinsic spins, a quantum property that determines how particles behave under rotations. Bosons, which include particles like photons and the Higgs boson, have integer spin values, while fermions, which include electrons and quarks, have half-integer spins. Supersymmetry proposes that these two fundamental classes of particles are intimately connected, with every boson having a fermionic superparticle and vice versa. This connection has profound implications for how we understand the forces of nature. In our current understanding, the electromagnetic weak and strong nuclear forces appear to be completely separate phenomena with very different strengths. But supersymmetry suggests that at sufficiently high energies that existed in the early universe, but are difficult to achieve in our laboratories, these forces might merge into a single, unified force. It's like discovering that what appear to be three different rivers actually flow from the same mountain spring, their apparent differences arising only because we observe them after they've traveled far from their common source. The search for supersymmetric particles has been one of the primary motivations behind building ever more powerful particle accelerators. The Large Hadron Collider at CERN was designed partly with the hope of producing superpartners in high-energy collisions, revealing the hidden mirror world that supersymmetry predicts. Scientists have looked for signs of squarks, selectrons, gluons, and neutralinos in the debris of proton-proton collisions, searching for the subtle signatures that would indicate the creation of these invisible partners. But after more than a decade of operation, the LHC has found no definitive evidence for supersymmetric particles. Each new analysis places tighter constraints on the possible properties of superpartners, pushing them to higher masses and weaker interactions than many theorists originally expected. This has led to what some physicists call the supersymmetry crisis, a growing tension between the theoretical appeal of the framework and the experimental difficulty of confirming its predictions. The absence of easily detectable superpartners doesn't necessarily mean supersymmetry is wrong, but it does suggest that if the theory is correct, it's more subtle than we initially hoped. Perhaps supersymmetry is broken in ways that make superpartners much heavier than ordinary particles, requiring even more powerful accelerators to produce them. Or perhaps the supersymmetric particles that could constitute dark matter interact so weakly with ordinary matter that they can't be produced in collider experiments at all. This situation illustrates one of the most challenging aspects of modern theoretical physics: the gap between what theories predict should be discoverable and what experiments can actually detect. Supersymmetry makes precise, testable predictions, but testing those predictions pushes the limits of human technology and ingenuity. We find ourselves in the position of detectives who have developed a compelling theory about a case, but lack the forensic tools needed to find the crucial evidence. Yet supersymmetry continues to captivate physicists because of its mathematical beauty and its potential to solve multiple puzzles simultaneously. Beyond providing dark matter candidates, supersymmetric theories offer potential solutions to the hierarchy problem: why gravity is so much weaker than other forces; the cosmological constant problem, why the vacuum energy of space doesn't cause the universe to expand catastrophically fast; and the unification of forces at high energies. The theory also connects to some of the most speculative ideas in modern physics, including string theory and extra dimensions. In these frameworks, supersymmetry isn't just a convenient mathematical trick, it's a fundamental aspect of reality that emerges naturally from the deeper structure of space and time. The visible universe would be just one facet of a much richer, more complex reality where supersymmetric partners play essential roles in maintaining the stability and consistency of physical laws. And that brings us to perhaps the most profound implication of supersymmetry. If it's real, then we live in a universe that's far more symmetric and balanced than appearances suggest. Every particle we can see and detect would be balanced by an invisible partner. Every force we experience would be part of a grander unified structure, and the apparent complexity of nature would emerge from underlying principles of extraordinary simplicity and elegance. Whether supersymmetry exists in nature, or remains forever a beautiful mathematical dream, its story reminds us that theoretical physics often leads us to consider possibilities that stretch the boundaries of imagination. The idea that reality might contain entire families of invisible particles connected to familiar matter through abstract mathematical symmetries challenges us to think beyond the limitations of direct observation and embrace the possibility that the universe is far stranger and more wonderful than we can currently perceive. The search beneath the mountains, 2 miles beneath the rolling hills of South Dakota, in what was once the deepest gold mine in the Western Hemisphere, scientists have constructed one of the most sensitive scientific instruments ever built: the Large Underground Xenon Experiment, all ellipsis, sits in a cavern carved from rock that's nearly 2 billion years old, shielded from cosmic rays by a mountain of stone and surrounded by detectors, so sensitive they can register the recoil of a single atomic nucleus struck by an invisible particle. This is the front line in humanity's search for dark matter, not in the vastness of space where its effects are most obvious, but here on Earth, deep underground, where the silence is so profound that scientists can listen for the whispered interactions between our world and the invisible universe that surrounds us. The logic behind going underground is both elegant and practical. The universe is constantly bombarded by cosmic rays, high-energy particles streaming in from deep space, from exploding stars, from the violent deaths of massive black holes billions of light-years away. When these cosmic rays strike the Earth's atmosphere, they create showers of secondary particles that rain down on the surface continuously, like invisible precipitation that never stops. For scientists trying to detect the incredibly rare interactions between dark matter and ordinary matter, cosmic rays are more than just background noise. They're like trying to hear a whisper in the middle of a thunderstorm. Every cosmic ray hit produces signals that can mimic the signatures scientists are looking for, making it nearly impossible to distinguish genuine dark matter interactions from cosmic ray imposters. But rock is an excellent shield against cosmic rays. Every foot of stone between the detector and the surface reduces the cosmic ray background by orders of magnitude, creating quieter and quieter conditions for the delicate art of dark matter detection. 2 miles underground, the cosmic ray background is reduced by a factor of more than 1,000,000, creating an environment quiet enough that individual particle interactions can be detected and studied. The detectors themselves are marvels of engineering precision. The most sensitive experiments use noble gases like xenon, cooled to extremely low temperatures and purified to extraordinary levels. Xenon is particularly appealing because it's dense, increasing the chances that a dark matter particle will interact with a xenon nucleus, chemically inert, reducing the risk of unwanted chemical reactions that could produce false signals, and responds to particle interactions by producing both light and electrical signals that can be precisely measured. Imagine a three-dimensional photograph that captures not just the image of an event, but also its energy, timing, and the precise way energy is deposited throughout the detector volume. Modern dark matter detectors create exactly this kind of multidimensional picture of every interaction that occurs within them, allowing scientists to distinguish between different types of particles based on their unique signatures. When a dark matter particle collides with a xenon nucleus, it should produce a very specific pattern, a single, clean recoil, with energy deposited uniformly in a small region of the detector. Cosmic rays and natural radioactivity, by contrast, tend to produce multiple interactions, irregular energy deposition patterns, or signals that occur simultaneously in different parts of the detector. It's like learning to recognize someone's handwriting. Once you know what to do for, genuine dark matter signatures should be distinguishable from imposters. But even with all these precautions, the expected rate of dark matter interactions is extraordinarily low. The most optimistic theoretical predictions suggest that a detector containing a ton of xenon might see only a few dark matter collisions per year. More pessimistic estimates suggest the rate could be much lower, requiring detectors that operate for decades to accumulate enough statistics to make a definitive detection. This has led to an escalating game of technological one-upmanship, with each new generation of experiments being larger, more sensitive, and more carefully shielded than the last. The current generation of detectors contains hundreds of kilograms of target material and achieves background levels that would have been unimaginable just a decade ago. The next generation will scale up to multi-ton detectors, increasing both the target mass and the statistical power needed to detect dark matter or rule out entire classes of candidates. The underground laboratories where these experiments operate have become international centers of scientific collaboration. The Sanford Underground Research Facility in South Dakota, the Gran Sasso Laboratory in Italy, the Snow Lab facility in Canada, and similar installations around the world host scientists from dozens of countries, all united in the quest to detect the invisible matter that shapes our universe. These laboratories also serve as testing grounds for technologies that push the boundaries of what's technically possible. Ultra-low background materials, cryogenic systems that maintain stable temperatures just above absolute zero for years at a time, electronics that can detect individual photons and electrons. All of these innovations emerge from the demanding requirements of dark matter detection, and often find applications in other fields. But perhaps most remarkably, these underground experiments represent humanity's attempt to detect particles that may have traveled unchanged through space for billions of years. A dark matter particle detected in a laboratory today might have been produced in the first moments after the Big Bang, survived the formation of galaxies and stars, witnessed the birth and death of countless solar systems, and finally ended its cosmic journey by colliding with a xenon nucleus in a detector built by curious humans on a small planet orbiting an ordinary star. The psychological aspect of this work is as fascinating as the technical challenges. Scientists operating these experiments must maintain extraordinary patience and discipline, running detectors for years at a time while seeing no obvious signals, constantly calibrating and cross-checking their instruments, and remaining alert for subtle effects that could easily be overlooked or misinterpreted. Every time one of these experiments reports null results, no definitive dark matter detection, it simultaneously represents both disappointment and progress. Each negative result rules out another region of parameter space, constraining the possible properties of dark matter particles and guiding the design of future experiments. It's a process of elimination on a cosmic scale, gradually narrowing down the possibilities, until we either detect dark matter or conclude that it interacts too weakly to be found with our current techniques. And that brings us to one of the most profound aspects of the underground search for dark matter. It represents humanity's attempt to touch the invisible universe that surrounds us. Every detector operation is an act of faith that the universe is comprehensible, that its secrets can be unlocked through careful observation and measurement, and that the same laws of physics that govern falling apples and planetary orbits also apply to particles, so elusive they rarely interact with ordinary matter throughout the entire age of the universe. Whether these underground experiments ultimately detect dark matter or constrain its properties so tightly that we must look elsewhere for answers, they represent something beautiful about human curiosity and ingenuity. In the deepest, quietest places we can create on Earth, we're listening for whispers from the cosmos, hoping to hear the faint voice of the invisible universe finally choosing to reveal itself. Dark matter. In the lab. In the depths of an abandoned mine shaft, nearly a mile beneath the Black Hills of South Dakota, scientists have built what might be the quietest place on Earth. Here, in the Sanford Underground Research Facility, detectors the size of washing machines sit in perfect stillness, waiting. They're waiting for something invisible to bump into them, just once. These aren't ordinary detectors. They're filled with liquid xenon, cooled to temperatures that would make Antarctica feel tropical. Each detector is surrounded by layers of lead and copper, shielded from cosmic rays and the natural radioactivity of the Earth itself. Because what they're hunting for is so incredibly elusive that even a single stray particle from space could mask its presence. The scientists down there are trying to catch dark matter, not with nets or traps, but by creating conditions so pristine that if a dark matter particle finally decides to interact with ordinary matter, they'll see the tiny flash of light it creates. It's like trying to catch snowflakes in a dark room, except the snowflakes are invisible, and you're not even sure they exist. Think about the dedication required here. Researchers spend years of their lives in these underground cathedrals of science, monitoring detectors that might never detect anything at all. It's the scientific equivalent of faith-building, enormous experiments based on mathematical equations and astronomical observations, hoping that somewhere in the darkness, matter we've never directly seen is floating all around us. The irony is beautiful. To find something that barely interacts with our world, we have to go to the places where our world barely exists, deep underground, far from the chaos of the surface. Scientists create pockets of almost perfect emptiness, hoping to glimpse the universe's most abundant mystery. And sometimes, just sometimes, these detectors do see something. A brief spark in the dark, but is it dark matter? Or just another false alarm? The answer to that question might reshape everything we think we know about reality. Other laboratories take a different approach entirely. At CERN, the European Organization for Nuclear Research, scientists are trying to create dark matter rather than detect it, using the Large Hadron Collider, that 27-kilometer ring of superconducting magnets buried beneath the French-Swiss border. They smash protons together at nearly the speed of light, hoping to recreate the conditions that existed just moments after the Big Bang. The theory is elegant. If dark matter particles exist, and if they were created in the early universe, then perhaps we can create them again, by colliding ordinary matter with enough energy. It's like trying to understand a symphony by smashing instruments together and listening for familiar notes in the chaos. But here's the beautiful puzzle. Even if we create dark matter particles in these collisions, we might never see them directly. They would fly away from the collision point, invisible and nearly untouchable, leaving behind only the faintest signature, missing energy that should have been there but somehow vanished into the darkness. This is science at its most poetic, building machines the size of cities to study particles we can't see, using the absence of evidence as evidence itself. It's a reminder that sometimes the most profound truths about our universe can only be discovered by what's not there, by the shadows cast by invisible light. Gravitational clues in cosmic structure. Imagine you're looking at a photograph of your family, but everyone's faces are hidden in shadow. You can still see their shapes, their outlines, the way they're standing together. You might not be able to see their expressions, but you can still tell they're there, still sense the bonds between them. This is exactly how astronomers first discovered dark matter, not by seeing it directly, but by observing its gravitational fingerprints on everything else. In the 1970s, astronomer Vera Rubin was doing something that sounds almost mundane, measuring how fast stars move around the centers of galaxies. It should have been routine work, like measuring how fast cars drive around a traffic circle, but what she found changed our understanding of the universe forever. Stars at the edges of galaxies were moving too fast, much too fast, according to Newton's laws, the same laws that keep the moon orbiting Earth, and predict exactly when eclipses will occur. These outer stars should have been moving slowly, lazily drifting around their galactic centers like distant planets in our solar system. Instead, they were racing around as if something invisible was pulling them along. It was like watching ice skaters on a frozen pond, expecting them to glide slowly around the edges, but instead seeing them whip around the perimeter as fast as the skaters near the center. The only way this makes sense is if there's more ice under the pond than you can see. Much more. Rubin's observation suggested that galaxies contain about 5 times more matter than we can observe with all our telescopes and instruments. 5 times more. Imagine discovering that your house weighs 5 times more than you thought, and you have no idea where the extra weight is hiding. That's the scale of the mystery Rubin uncovered. But the story gets even more intriguing when we zoom out from individual galaxies to look at the cosmic web, the largest structures in the universe. Through powerful telescopes, we can see that galaxies aren't scattered randomly through space like stars in the night sky. They're arranged in an intricate pattern, long filaments of light connected by massive clusters, with vast empty regions called cosmic voids in between. This cosmic web looks remarkably like soap bubbles, or the foam on top of your morning coffee, delicate strands of matter, creating pockets of emptiness. But here's the remarkable thing. When scientists run computer simulations of how the universe should have evolved from the nearly uniform state it was in just after the Big Bang, they can only recreate this beautiful web-like structure if they include dark matter in their calculations. Without dark matter, their simulated universes look nothing like our own. Galaxies form too late, or not at all. The cosmic web becomes a cosmic mess. It's as if dark matter provides the invisible scaffolding upon which all visible matter builds its grand architecture. Think of it like this. Imagine you're trying to understand why a city grew the way it did, why certain neighborhoods developed where they did, why the main roads follow particular paths. You might not be able to see the original rivers that were filled in, or the ancient paths that determined where the first settlers built their homes. But the ghost of that invisible infrastructure still shapes everything you can see today. Dark matter might be the universe's invisible infrastructure, the hidden foundation that allowed galaxies to form, stars to ignite, and ultimately planets, like Earth, to exist. We are, in a very real sense, children of dark matter's gravitational embrace. Alternative theories. Modified gravity. But what if we've been thinking about this all wrong? What if the mystery isn't about missing matter but about misunderstanding gravity itself? This is where our story takes a fascinating turn into the realm of scientific rebellion and elegant alternatives. In the early 1980s, Israeli physicist Mordechai Milgrom proposed something audacious. Maybe, he suggested, Newton's laws don't work the same way in all situations. Maybe gravity behaves differently when it's very weak, like at the edges of galaxies where stars are moving too fast. He called his idea modified Newtonian dynamics, or MOND. It's a beautiful thought. Perhaps gravity isn't the universal constant we imagined. Maybe it's more like water, which behaves one way when it's flowing fast down a river, and completely differently when it's barely trickling through sand. Maybe gravity, when it becomes very weak across vast cosmic distances, starts following different rules. Mondide is elegant in its simplicity. Instead of inventing an entirely new type of matter to explain why galaxy rotation curves look wrong, Milgrom suggested we modify our understanding of gravity itself. It's like realizing that your car isn't heavier than you thought. Your speedometer just reads differently at certain speeds. The theory makes specific, testable predictions. It says that in regions where gravitational acceleration is below a certain threshold about 10 trillion times weaker than Earth's gravity, Newton's inverse square law begins to break down. Gravity becomes stronger than expected, which would explain why stars at the edges of galaxies move faster than they should. And here's the remarkable thing. MOND actually works quite well for many galaxies. It predicts their rotation curves with stunning accuracy, sometimes better than dark matter models do. It's as if Milgrom discovered a hidden law of nature that had been whispering its existence through the motion of distant stars. But science is never simple, and MOND faces its own challenges. While it works beautifully for individual galaxies, it struggles to explain larger cosmic structures, galaxy clusters, the cosmic microwave background, the way light bends around massive objects. It's like having a key that perfectly opens one lock, but doesn't quite fit any of the others. There's something almost philosophical about this debate. Are we missing most of the universe's matter, or do we misunderstand one of nature's most fundamental forces? Both possibilities are humbling. Both suggest that after centuries of scientific progress, we're still like children playing on the beach of cosmic understanding, occasionally finding a prettier shell while the vast ocean of knowledge stretches before us. Perhaps the most beautiful aspect of this scientific controversy is how it reflects the nature of discovery itself. Sometimes the greatest insights come not from finding new things, but from questioning our most basic assumptions. MOND reminds us that even gravity, the force we experience every moment of our lives, might still hold surprises. MOND and the limits of Newton. Isaac Newton thought he had figured out the universe. In 1687, he published his Principia Mathematica, which described gravity as a force that acts the same way everywhere, from apples falling from trees to planets orbiting the sun. For over 3 centuries, Newton's laws worked so perfectly that they became synonymous with physical truth itself. But here's something wonderful about science. It's always willing to admit when even its greatest heroes might have been incomplete. Newton's laws are still correct for most situations. They'll still get a spacecraft to Mars with pinpoint accuracy, but they might not tell the whole story about gravity in the far reaches of galaxies. MOND suggests that Newton's laws are like a local weather forecast, perfectly accurate for your immediate surroundings, but maybe not precise enough to predict what's happening on the other side of the world. When gravitational acceleration becomes extremely weak, weaker than anything we experience on Earth, MOND proposes that gravity starts following a different mathematical relationship. Instead of force being proportional to acceleration, as Newton suggested, MOND says that in these ultra-weak gravity regions, force becomes proportional to acceleration squared. It sounds like a small change, just adding an exponent, but it has profound implications for how matter behaves at galactic scales. Think of it like learning that water doesn't always flow downhill the same way. At certain temperatures and pressures, water might flow uphill, or sideways, or in spirals. The basic idea of water flowing remains the same, but the rules governing that flow become more complex and beautiful. The mathematical elegance of MOND is compelling. It introduces just one new constant, a fundamental acceleration scale below which gravity behaves differently. This constant, roughly 10 to the power of negative 10 meters per second squared, might be as fundamental to the universe as the speed of light or Planck's constant. But MOND also highlights something profound about the nature of scientific knowledge. Newton's laws weren't wrong, they were incomplete. They describe reality perfectly within a certain range, just as a map of your neighborhood is perfectly accurate for finding your way home, even though it doesn't show the entire world. This is how science progresses. Not by throwing out old ideas entirely, but by discovering the boundaries where those ideas need to be expanded or refined. Einstein didn't prove Newton wrong. He showed that Newton's laws are a special case of something larger and more beautiful. MOND might represent another step in this ongoing refinement of our understanding. The controversy surrounding MOND also illustrates something beautiful about scientific culture. Here we have 2 competing explanations for the same observations: invisible matter versus modified gravity. Both have evidence in their favor, Both face challenges, and both communities of scientists are working passionately to test their ideas against reality. This isn't a weakness of science, it's its greatest strength, the willingness to hold multiple possibilities simultaneously, to let evidence rather than preference determine truth, to remain humble in the face of cosmic mystery. Whether matter or dark matter ultimately proves correct, the process of testing these ideas against observations is already teaching us profound lessons about the nature of our universe. Dark matter or dark illusion. Sometimes the most important question in science isn't how does this work, but does this actually exist? We're now at the heart of one of the most fundamental debates in modern cosmology. Is dark matter a real substance filling the universe, or are we chasing shadows cast by our incomplete understanding? This question touches something deep about the nature of scientific discovery itself. How do we distinguish between discovering something genuinely new about reality versus discovering the limits of our current theories? It's like the difference between finding a new room in your house versus realizing you've been misreading the blueprint all along. The case for dark matter's reality is compelling. Multiple independent lines of evidence all point toward the same conclusion. There's about 5 times more matter in the universe than we can see. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the formation of large-scale structure, all of these phenomena seem to require additional matter that interacts gravitationally, but remains invisible to light. It's like a cosmic detective story where multiple witnesses, who have never met each other, all describe the same mysterious suspect. The gravitational effects we observe are so widespread and consistent that many scientists find it hard to believe they could all be explained by modifications to gravity alone. But the case for dark matter being an illusion is equally fascinating. What if we're like ancient astronomers who invented increasingly complex models to explain planetary motion, adding epicycles upon epicycles, when the real solution was much simpler? What if dark matter is our generation's version of the luminiferous ether, that hypothetical substance 19th century physicists thought filled all of space? The history of science is filled with substances that seemed absolutely necessary until they suddenly weren't. Phlogiston was supposed to explain combustion. Caloric was supposed to explain heat. The ether was supposed to carry light waves. All seemed obvious and necessary to the scientists of their time, yet all eventually proved to be illusions born from incomplete understanding. Perhaps dark matter is similar, a placeholder we've invented to fill the gaps in our knowledge, like drawing dragons on the unexplored edges of ancient maps. Maybe the real answer lies not in finding new types of matter, but in discovering new aspects of space, time, or gravity that we haven't yet imagined. There's something beautifully humbling about this uncertainty. Here we are, in the 21st century, with telescopes that can see to the edge of the observable universe, with particle accelerators that can recreate conditions from the first moments after the Big Bang, and yet we might be fundamentally wrong about what makes up most of our universe. This uncertainty isn't a failure of science. It's science working exactly as it should. The willingness to question our most basic assumptions, to hold multiple possibilities simultaneously, to let evidence rather than intuition guide our understanding. Whether dark matter proves to be the universe's dominant substance, or the 21st century's greatest scientific mirage, the search itself is teaching us profound lessons about the nature of reality. The debate also highlights something beautiful about scientific humility. The greatest scientists throughout history have been those willing to admit when they don't know something, when their theories might be incomplete, when the universe might be stranger and more wonderful than they first imagined. Simulations of a dark universe. Deep in the basement of a research facility, a supercomputer hums quietly as it creates universes, not real ones of course, but mathematical representations so detailed and vast that they contain billions of virtual galaxies, each with their own stars, their own histories, their own gravitational dances across cosmic time. These aren't video game worlds or science fiction fantasies, they're serious scientific tools, virtual laboratories where cosmologists can test their theories about how the universe works. And at the heart of most of these simulations lies dark matter, invisible threads weaving through space, pulling ordinary matter into the familiar patterns we see in the night sky. The process is breathtakingly ambitious. Scientists start with the conditions that existed just a few 100,000 years after the Big Bang, when the universe was nearly uniform, just tiny fluctuations in density, like ripples on a perfectly calm pond. Then they let their virtual universe evolve forward in time, following the laws of physics, as we understand them, watching 13 billion years of cosmic history unfold in fast forward. Without dark matter in these simulations, something remarkable happens. The universe stays boring. Those tiny initial fluctuations grow, but slowly, too slowly. By the time the simulated universe reaches an age equivalent to our own, it looks nothing like the rich, complex cosmos we actually observe. Galaxies form late, if at all. The cosmic web, that beautiful interconnected network of filaments and voids, never develops its intricate structure. But add dark matter to the simulation, and magic happens. The invisible matter acts like a gravitational scaffolding, pulling ordinary matter into increasingly complex patterns. Dark matter halos form first. Invisible cosmic architecture that provides the framework for galaxy formation. Then, ordinary matter falls into these dark matter wells, cooling and condensing into the first stars. It's like watching a time-lapse video of a city being built. First, invisible foundations are laid. You can't see them directly, but they determine where everything else will go. Then the visible infrastructure appears. Roads, buildings, light. The final result looks chaotic and organic, but it's actually following the invisible blueprint laid down by the dark matter scaffolding. The most successful simulations, the ones that best match our observations of the real universe, typically assume that dark matter makes up about 27% of everything that exists. Ordinary matter, the stuff that makes up stars, planets, and us, accounts for less than 5%. The rest is dark energy, but that's another mystery entirely. These simulations have become so sophisticated that scientists can zoom into individual galaxies within their virtual universes and study how dark matter affects star formation, galaxy mergers, and the creation of supermassive black holes. They can run the same simulation multiple times with slightly different assumptions and see how sensitive their conclusions are to various parameters. But perhaps the most beautiful aspect of these cosmic simulations is what they reveal about the nature of emergence. Complex structures, galaxies, galaxy clusters, the cosmic web itself, emerge naturally from relatively simple initial conditions and physical laws. You don't need to program galaxies into the simulation. They form spontaneously when dark matter and ordinary matter interact over cosmic time. It's reminiscent of how flocks of birds create complex flowing patterns without any central coordination, or how individual water molecules collectively create the mesmerizing patterns of turbulence in a stream. Simple rules, operating over vast scales of space and time, give rise to the magnificent complexity we see in the universe around us. The role of dark matter in galaxy formation. Picture the universe as a vast, dark ocean immediately after the Big Bang. Nearly smooth, nearly uniform, with only the faintest ripples disturbing its surface. Now imagine that within this cosmic sea, invisible currents begin to flow, creating subtle whirlpools and eddies that slowly grow stronger over millions of years. This is how dark matter may have shaped everything we see today. Long before the first stars ignited, before galaxies painted their spiral arms across the cosmos, dark matter was quietly building the invisible architecture that would guide the formation of all visible structure in the universe. The story begins in the cosmic dark ages, when the universe was filled with hydrogen and helium gas, but no stars had yet formed to light the darkness. During this time, dark matter was already hard at work, its gravitational influence slowly drawing itself into increasingly dense clumps. These dark matter halos, as astronomers called them, became the gravitational wells into which ordinary matter would eventually fall. Think of dark matter halos as invisible valleys in the gravitational landscape of space. Ordinary matter, like water flowing downhill, naturally collects in these valleys. But unlike water, this cosmic gas doesn't just pool. It compresses and heats up until it reaches the temperatures and densities necessary for nuclear fusion. The first stars are born. This process is beautifully hierarchical. Small dark matter halos merge to form larger ones, which merge to form larger ones still. Each merger brings its own collection of gas and stars, building increasingly massive and complex galactic systems. It's like watching a cosmic symphony, where dark matter provides the underlying rhythm, while ordinary matter plays the melody we can actually hear. The Milky Way galaxy we call home is thought to sit within a dark matter halo, roughly 10 times more massive than all the visible stars and gas we can observe. This invisible halo extends far beyond the edge of our galaxy's visible disk, creating a vast spherical cocoon of dark matter that keeps our galaxy gravitationally bound. But dark matter's role in galaxy formation goes beyond just providing gravitational scaffolding. Computer simulations suggest that the properties of dark matter, how it interacts with itself, how it clumps together, how it responds to gravitational forces determine many of the characteristics we observe in real galaxies. The rotation curves that first led astronomers to suspect dark matter's existence. They're naturally explained. If galaxies are embedded in these massive dark matter halos, the fact that spiral galaxies maintain their graceful arms over billions of years, despite the differential rotation that should wind them up, dark matter provides the gravitational stability that keeps these structures intact. Even more remarkably, the diversity of galaxy types we observe, from dwarf ellipticals to massive spirals to giant ellipticals, might be largely determined by the properties of their dark matter halos. The mass of the halo, its concentration, its merger history, all of these invisible factors shape the visible galaxy that forms within it. This is one of the most beautiful aspects of the dark matter hypothesis. It suggests that the cosmos has two interconnected stories unfolding simultaneously. There's the story we can see, stars being born and dying, galaxies colliding and merging, black holes growing and feeding. But underneath it all is an invisible story of dark matter halos growing and evolving, providing the gravitational foundation for everything visible. It's like discovering that your favorite piece of music has been accompanied all along by an instrument you couldn't hear, one that provides the harmonic structure that makes the melody possible. Dark matter might be the universe's baseline, subtle and often unnoticed, but absolutely essential to the cosmic symphony we observe. Black holes and cosmic glue. At the center of our galaxy lurks something extraordinary. A supermassive black hole called Sagittarius A, with a mass 4 million times greater than our Sun. It sits there like a gravitational lighthouse, its presence revealed by the frantic orbital dance of nearby stars. But here's a fascinating question that keeps cosmologists awake at night. What came first? The galaxy or the black hole? This might seem like a cosmic version of the chicken and egg problem, but it touches on one of the most intriguing relationships in the universe: the connection between dark matter, galaxy formation, and the growth of supermassive black holes. These three phenomena are so intertwined that understanding one requires understanding them all. Current thinking suggests that dark matter halos form first, creating the gravitational wells into which ordinary matter falls. As gas accumulates in these dark matter valleys, some of it eventually makes its way to the very center, where extreme conditions allow the formation of the first black holes. These seed black holes then grow by accreting more matter and merging with other black holes, eventually becoming the supermassive monsters we observe at the hearts of most large galaxies. But the relationship isn't one way. As these central black holes grow, they begin to influence the entire galaxy around them. They can heat up nearby gas, preventing it from forming stars. They can launch powerful jets of particles that sculpt the galaxy's structure across thousands of light years. In a very real sense, the black hole and its host galaxy co-evolve, each shaping the other's growth and development. Dark matter plays a crucial role in this cosmic dance. The dark matter halo provides the stable gravitational foundation that allows both the galaxy and its central black hole to grow over billions of years. Without this invisible scaffolding, galaxies might be torn apart by their own internal dynamics, or by interactions with neighboring galaxies. There's something almost symbiotic about these relationships. The dark matter halo captures and concentrates ordinary matter. Some of this matter forms stars, lighting up the galaxy and making it visible to our telescope. Other matter feeds the central black hole, powering the jets and winds that regulate further star formation. It's a complex feedback system where invisible dark matter, visible stars and invisible black holes all influence each other's evolution. Recent observations have revealed something even more intriguing. There appears to be a tight relationship between the mass of a galaxy's central black hole and the total mass of its dark matter halo. Galaxies with more massive dark matter halos tend to host more massive black holes. This correlation is so strong that it suggests a deep connection between these two dark components of galaxies. Think about how remarkable this is. Dark matter, which barely interacts with ordinary matter at all, somehow manages to regulate the growth of black holes, which are among the most extreme objects in the universe. It's like discovering that the foundation of your house determines not just its size and shape, but also the specific characteristics of every piece of furniture inside it. This relationship might help explain one of the great puzzles of galaxy formation, why there's such a wide variety of galaxy types and sizes. Perhaps the properties of each galaxy's dark matter halo, its mass, its concentration, its merger history, determine not just how many stars form, but also how massive the central black hole becomes, and how it influences the galaxy's subsequent evolution. The interplay between dark matter galaxies and black holes also highlights something beautiful about cosmic evolution. Nothing in the universe evolves in isolation. Every object, from the smallest asteroid to the largest galaxy cluster, is part of an interconnected web of gravitational relationships that stretches across space and time. Dark matter versus dark energy. Imagine the universe as a cosmic tug-of-war, with two mysterious forces pulling in opposite directions. On one side, there's dark matter, invisible, but ever-present, trying to pull everything together with its gravitational embrace. On the other side, there's dark energy, even more mysterious and powerful, pushing space itself apart and accelerating the universe's expansion. This is one of the most extraordinary discoveries in the history of astronomy. Not only is most of the universe's matter invisible to us, but most of the universe's energy is also completely unknown. Together, dark matter and dark energy make up about 95% of everything that exists. We are living, quite literally, in a universe that is almost entirely dark, to our understanding. But these two dark components couldn't be more different in their effects. Dark matter acts like cosmic glue, clustering together and pulling ordinary matter into the galaxies and stars we see around us. It's the reason galaxies can exist at all, providing the gravitational scaffolding that prevents them from flying apart as they rotate. Dark energy, on the other hand, acts like cosmic anti-glue. It doesn't cluster or clump like matter does. Instead, it fills all of space uniformly, creating a gentle but persistent outward pressure that causes the universe's expansion to accelerate. The more space expands, the more dark energy there is, creating a kind of cosmic feedback loop that drives ever faster expansion. The discovery of dark energy came as a complete shock to astronomers in the 1990s. Two teams of scientists were studying distant supernovae, stellar explosions, so bright they can be seen across billions of light-years, expecting to measure how much the universe's expansion was slowing down due to gravity. Instead, they found that the expansion was speeding up. It was like throwing a ball into the air and watching it accelerate upward instead of slowing down and falling back to Earth. The discovery was so unexpected that both teams initially thought they had made a mistake, but repeated observations confirmed the impossible. The universe's expansion is accelerating, driven by some form of energy that pervades all of space. This creates a fascinating cosmic timeline. In the early universe, when matter was more densely packed, gravity dominated, and the expansion was indeed slowing down. But as the universe expanded and matter became more dilute, dark energy began to take over. About 5 billion years ago, roughly when our solar system was forming, dark energy became the dominant force, and the universe's expansion began to accelerate. The implications are profound. If dark energy continues to dominate, the universe will expand forever, becoming increasingly cold and empty. Galaxies will drift apart until they can no longer see each other. Stars will burn out, black holes will evaporate, and the universe will end not in a fiery collapse but in what cosmologists poetically call the heat death, maximum entropy, and perfect eternal darkness. But here's what makes this story even more intriguing. Dark matter and dark energy might not be completely separate phenomena. Some theories suggest they could be different aspects of the same underlying physics. Perhaps what we call dark energy is actually a property of space itself, while what we call dark matter is a consequence of how gravity behaves on cosmic scales. The relationship between these two dark components also raises deep questions about the nature of our universe. Why do dark matter and dark energy have roughly the same density today, when they evolve so differently over cosmic time? This coincidence problem suggests that either we're living at a very special moment in cosmic history, or there's some deeper connection between these phenomena that we don't yet understand. Could we be made of it? Here's a thought that might make you pause as you settle into sleep tonight. What if dark matter isn't just around us, but within us? What if every breath you take, every heartbeat, every thought that crosses your mind is somehow touched by particles that make up the vast majority of our universe's matter? This isn't science fiction, it's a genuine scientific question that touches on some of the deepest mysteries about consciousness, life, and our place in the cosmos. If dark matter truly makes up about 27% of everything that exists, and if it's distributed throughout space, then dark matter particles are almost certainly passing through your body right now. The numbers are staggering. Some calculations suggest that billions of dark matter particles flow through every square centimeter of your body every second. They pass through you like ghostly rivers, barely interacting with the atoms that make up your cells, your DNA, your neural networks. You are, in a very real sense, swimming in an ocean of invisible matter. But could this constant bath of dark matter particles affect biological processes? Could they influence the delicate quantum processes that occur within living cells? Some scientists have proposed that dark matter interactions, however rare, might play a role in genetic mutations, in the random processes that drive evolution, perhaps even in the quantum events that some theories suggest might be important for consciousness. The idea isn't as far-fetched as it might sound. We already know that cosmic rays, high-energy particles from space, can occasionally cause genetic mutations by striking DNA molecules. If dark matter particles occasionally interact with biological matter, they might have subtle but measurable effects on living systems. Some researchers have even suggested that life itself might have evolved ways to exploit dark matter interactions. Perhaps certain biological processes are sensitive to the tiny energy deposits that dark matter particles occasionally leave behind. Perhaps evolution has found ways to use the universe's most abundant form of matter as a subtle information channel. There's something almost poetic about this possibility. If dark matter influences biological processes, then every living creature on Earth, every tree, every microbe, every bird that flies overhead, would be connected to the vast cosmic web of dark matter that stretches across the universe. We would be not just made of star stuff, as Carl Sagan famously said, but also made of dark stuff. The connection might run even deeper. Some theories of consciousness suggest that quantum processes in the brain, tiny events at the molecular level, might be important for awareness, memory, and thought. If dark matter occasionally influences these quantum processes, then your thoughts, your dreams, your very sense of self, might be subtly shaped by particles that also determine the large-scale structure of galaxies. Imagine that. The same invisible matter that holds the Milky Way together might also be involved in holding your memories together. The same dark particles that guided the formation of galaxy clusters billions of years ago might occasionally nudge the chemical reactions that create your thoughts tonight. Of course, these are highly speculative ideas. The interactions between dark matter and ordinary matter are thought to be incredibly weak, so weak that detecting them requires building enormous ultra-sensitive detectors buried deep underground. The chance that such weak interactions could significantly influence biological processes is very small, but even if dark matter doesn't directly affect biological systems, there's still something profound about our relationship to it. We exist within a universe that is mostly invisible to us, surrounded by forms of matter and energy that we're only beginning to understand. Our very existence, the formation of Earth, the evolution of life, the development of intelligence capable of pondering these questions, all of this depends on the gravitational scaffolding provided by dark matter. Is dark matter a portal to new physics? Sometimes the most important discoveries in science aren't answers, they're better questions. Dark matter might not just be a missing piece of our current cosmic puzzle, it might be a doorway into entirely new realms of physics, new ways of understanding the fundamental nature of reality itself. Consider the profound implications if dark matter truly exists as a new category of matter. This would mean that the atoms that make up your body, the air you breathe, the earth beneath your feet, all the stars you can see in the night sky, all of this represents less than 5% of what actually exists. We would be like inhabitants of a tiny island, completely unaware of the vast continents that surround us. But the implications run deeper than just discovering new types of particles. Dark matter might be revealing that our entire framework for understanding the universe needs to be expanded. Perhaps there are whole sectors of physics that operate alongside our familiar world but remain largely invisible to us. Some theoretical physicists have proposed that dark matter might be the lightest particle in an entire dark sector, a parallel physics that mirrors our own but interacts with it only through gravity. Just as our visible world contains electrons, protons, neutrons, and dozens of other particles, the dark sector might contain its own rich zoo of dark particles with their own forces and interactions. This isn't just speculation. Theories like supersymmetry predict the existence of particles for every particle we know about. The lightest of these supersymmetric particles might be stable and interact only weakly with ordinary matter, perfect candidates for dark matter. If supersymmetry is real, then discovering dark matter would simultaneously confirm one of the most elegant theoretical frameworks in modern physics. Other theories suggest even more exotic possibilities. Maybe dark matter particles are their own antiparticles, occasionally annihilating with each other to produce brief flashes of gamma rays that we might detect with sensitive space telescopes. Maybe dark matter exists in extra dimensions of space that we can't directly perceive, influencing our three-dimensional world only through gravity. Some of the most intriguing ideas propose that dark matter might be a window into the quantum nature of gravity itself. Perhaps what we interpret as dark matter particles are actually quantum fluctuations in the fabric of space-time, or manifestations of gravity operating according to rules we haven't yet discovered. The search for dark matter has already pushed technology to extraordinary limits. The detectors buried deep underground are among the most sensitive instruments ever built, capable of detecting energy deposits so small they rival the quantum fluctuations of empty space itself. The particle accelerators designed to create dark matter are probing energy scales that existed only in the first moments after the Big Bang. This technological revolution has applications far beyond cosmology. The ultra-pure materials developed for dark matter detectors are finding uses in quantum computing. The statistical techniques developed to separate dark matter signals from background noise are being applied to medical imaging and artificial intelligence. The search for dark matter is not just expanding our knowledge of the universe, it's expanding our technological capabilities in ways that benefit all of humanity. But perhaps the most profound implication of dark matter is philosophical. If it exists, it suggests that reality is far stranger and more wonderful than we ever imagined. We would be living in a universe where most of matter is invisible, where entire sectors of physics operate beyond our direct perception, where the very structure of galaxies depends on substances we can barely detect. This humility in the face of cosmic mystery is one of science's greatest gifts. The willingness to admit that we might be profoundly ignorant about the fundamental nature of our universe. The excitement of discovering that reality is more complex and beautiful than our theories predicted. Dark matter reminds us that the universe still holds secrets we haven't even begun to guess at. What if dark matter doesn't exist? But let's pause for a moment and consider the other possibility, one that's equally profound and perhaps even more unsettling. What if dark matter is simply wrong? What if we've spent decades building elaborate theories, constructing expensive experiments, and proposing exotic new physics to explain something that isn't actually there? This wouldn't be the first time in scientific history that a widely accepted idea turned out to be a beautiful mistake. The luminiferous ether seemed absolutely necessary to 19th century physicists. How else could light waves travel through the vacuum of space? Phlogiston explained combustion so elegantly that it took decades for chemists to accept that burning was actually about gaining oxygen, not losing some mysterious fire substance. If dark matter doesn't exist, it would mean that our understanding of gravity itself is incomplete. Maybe Einstein's general relativity, like Newton's laws before it, is accurate within a certain range, but breaks down under extreme conditions. Maybe gravity becomes stronger at very large scales, or behaves differently when matter densities are extremely low. The implications would be staggering. Every galaxy rotation curve, every gravitational lensing observation, every feature of the cosmic microwave background that we currently explain with dark matter would need a new interpretation. The standard model of cosmology, our best current description of how the universe evolved from the Big Bang to today, would require fundamental revision. But here's what makes this possibility so intriguing. It might actually be simpler than the dark matter hypothesis. Instead of inventing entirely new types of matter that make up most of the universe, we would need only to modify our understanding of one fundamental force. It's a reminder of Occam's razor, the principle that simpler explanations are often better. Some versions of modified gravity theories make predictions that are testable and different from dark matter models. Future observations might be able to distinguish between these possibilities. Perhaps studies of galaxy mergers, or precise measurements of gravitational waves, or observations of the cosmic microwave background will finally tell us whether we live in a universe filled with invisible matter or governed by modified gravity. The uncertainty itself is remarkable. Here we are in the 21st century, with telescopes that can peer back to within a few 100,000 years of the Big Bang, with particle accelerators that can recreate conditions from the first moments of cosmic time, and yet we remain genuinely unsure about what makes up most of our universe. This uncertainty isn't a failure of science, it's science working exactly as it should. The willingness to hold multiple possibilities simultaneously, to test competing ideas against observation, to remain humble in the face of evidence. Whether dark matter exists or not, the process of searching for it has already taught us profound lessons about the nature of galaxies, the behavior of gravity, and the evolution of cosmic structure. If dark matter turns out to be real, we'll have discovered that the universe is filled with entirely new forms of matter that interact through forces we don't yet understand. If it turns out to be wrong, we'll have discovered that gravity itself is far more subtle and complex than we realized. Either way, we'll have learned something fundamental about the cosmos. There's something beautiful about this moment in scientific history. We're like explorers standing at the edge of a vast, unknown continent, not yet sure what we'll find, but certain that the journey of discovery will transform our understanding of the world. The mystery of dark matter represents one of the last great frontiers in our comprehension of the physical universe. Still searching the shadows, as our journey through the cosmos draws toward its close, it's worth reflecting on where we find ourselves in this greatest of all detective stories. We've explored underground laboratories where scientists wait in cathedral-like silence for invisible particles to reveal themselves. We've journeyed through computer simulations of entire universes, watching dark matter weave the cosmic web across billions of years. We've contemplated the possibility that most of reality might be hidden from our direct perception, operating through forces and interactions we're only beginning to glimpse. And yet, for all our sophisticated theories and elegant experiments, the fundamental question remains: does dark matter really exist? After decades of searching, we still don't have a definitive answer. This might seem disappointing, but it's actually one of the most exciting aspects of modern science. We're living through a period of genuine cosmic mystery, when our most basic assumptions about the universe are still being tested. The search for dark matter has already transformed our understanding of the cosmos in profound ways. It's shown us that the universe is far more dynamic and interconnected than we once imagined. It's revealed that the formation of galaxies, stars, and ultimately life itself might depend on invisible scaffolding that shapes the architecture of space and time. Whether dark matter exists as exotic particles, or whether it represents new physics in the behavior of gravity itself, or whether it's something else entirely that we haven't yet imagined, the answer will fundamentally change how we see our place in the universe. We might be surrounded by realms of physics that operate beyond our direct perception. We might be missing most of the matter that exists. We might be misunderstanding one of the most fundamental forces in nature. Any of these possibilities would be remarkable. All of them would be humbling. The scientists working in those underground laboratories, analyzing data from space telescopes, running simulations on supercomputers, they're not just searching for particles or testing theories, they're participating in one of humanity's greatest adventures, the quest to understand our cosmic home. Every negative result, every puzzling observation, every failed detection brings us closer to the truth. Even if that truth turns out to be different from what we expected, there's something profoundly moving about this scientific humility. The willingness to spend careers searching for something that might not exist. The readiness to question our most fundamental assumptions about reality. The courage to admit that after centuries of scientific progress, we might still be profoundly ignorant about the basic nature of our universe. Perhaps the most beautiful aspect of the dark matter mystery is what it reveals about the process of discovery itself. Science isn't just about finding answers, it's about learning to ask better questions. Whether dark matter is real or illusory, whether it's made of exotic particles or emerges from modified gravity, the journey of searching for it has expanded our vision of what's possible. As you drift towards sleep tonight, consider this. You're floating through space, on a small planet, orbiting an ordinary star, in a galaxy that might be held together by invisible matter we've never directly detected. The atoms in your body were forged in the hearts of ancient stars, but they might represent less than 5% of what actually exists in the cosmos around you. We are, all of us, children of the universe's greatest mystery. Whether that mystery is called dark matter, modified gravity, or something we haven't yet imagined, we're participants in a cosmic story whose ending we don't yet know. And that, perhaps, is the most wonderful thing of all. The universe still holds secrets. The darkness still whispers with possibilities we haven't learned to hear. And somewhere, in laboratories deep underground or in the gravitational dance of distant galaxies, the answers are waiting to be discovered. Sweet dreams, fellow travelers in this dark and magnificent cosmos. The search continues, and the mystery deepens, and the universe grows ever more beautiful in its complexity. The end. In the depth of winter, I finally learned that there was in me an invincible summer. Albert Camus. Just as Camus found light within darkness, perhaps our search for dark matter will ultimately illuminate not just the hidden structure of the universe, but the luminous power of human curiosity itself. The cosmos keeps its secrets well, but we keep asking questions, and in that questioning, in that endless reaching toward understanding, we find something as fundamental as dark matter itself, the irrepressible human drive to comprehend our place in the vast, mysterious whole.